Section 8.2 is integration by parts. Everything that we did in Section 8.1, you technically could have done using techniques that you learned in Cal 1. This is the first section for an integration technique that's unique to Cal 2. And the integration by parts rule comes from the product rule for derivatives. So if f and g are differentiable functions of x, the product rule says that the derivative with respect to x of f times g of x is equal to the derivative of f times g plus f times the derivative of g. In order to simplify things, I'm going to do some substitutions here. Let's let u be equal to f of x, then du will be equal to f prime of x. And v, we're going to let be equal to g of x, so dv will be equal to g prime of x. Now, in algebra you learned that you can pretty much do anything you want to an equation as long as you do the same thing to both sides of the equation. So what I'm going to do is I'm going to integrate both sides of this equation. I'll do the substitutions in a minute. I'm going to work with this right now. The integral of a derivative is going to be the integrand, this f of x times g of x. And then we'll say that's equal to the integral of f prime of x, g of x, plus the integral of f of x, g prime of x. Now I'm allowed to do this because I can distribute an integral across addition. Now I'm going to plug in these u's and du's and v's and dv's. So this says that I get u v equals the integral of the derivative of f is du and g is v. So that's going to be v du plus the integral of u dv. If I were to solve this equation for u dv, I would subtract the integral of v du from both sides of the equation. So I'm going to subtract the integral of v du from both sides of this equation. My equal sign is right there. And when I do that, that's going to give me the integral of u dv is equal to u v minus the integral of v du. Now I want this u dv on the left, so I'm going to rewrite that as the integral of u dv is equal to uv minus the integral of v du. And this is what we call our integration by parts formula. And we know that it works because we took it from the rule for the product rule for derivatives. So we've algebraically manipulated this so that if I have an integral that's in this form, then it will be equal to this. This is a new technique that we're going to use. You need to memorize this integration by parts formula. And the quicker you do, the better your life will be. Now I'm going to show you how to use this integration by parts formula. Whenever you encounter a problem that it looks like you can't integrate because it's mixing, like in this case, an algebraic function with a transcendental function, try using the integration by parts formula. Notice that this is in the form, the integral of u dv, if I let this whole thing here be equal to dv. So the parts that we're looking at are going to be as follows. We're going to let u be equal to x. That means that du is going to be equal to dx. And then dv, we would say, would be equal to sine of 5x dx, which means that v, when I integrate that, I get negative 1/5 cosine 5x. These are the parts. So u is equal to x, and that comes from this part right here. And dv is this part right here, and that came from this part. These two things together make up the parts for the integration by parts. So we have the integral of u dv is going to be equal to, that formula says, uv minus the integral of v du. So when I rewrite this, I get the integral of x sine 5x dx is equal to x times negative 1/5 cosine 5x, that's the v, minus the integral of v, which is negative 1/5 cosine 5x, du, which is dx. The u parts are right here and right here. The v parts are right here. This is v, and this is v. So now it's just a matter of cleaning things up. So x times negative 1/5 cosine 5x, I'm going to write as negative x over 5 cosine 5x. And then I'm going to pull that negative 1/5 out, which makes this plus 1/5, the integral of cosine 5x dx. So I'm not done with the problem yet. I still have an integral in the problem, so I still need to integrate. Now when I integrate, I'm just going to copy down the front part and just carry that down to the next line. And the integral of cosine is what? Is sine. Leave the angle alone. And what about that 5? What effect does that have when I integrate? It's a constant multiple of 1/5 in front of that. And then I put plus c because now I've integrated this cosine. This right here is the integral of cosine 5x dx. Do you see that? Now I'm ready to clean this up and write my final answer. That's going to give me negative x over 5 cosine 5x plus 1 over 25, because 1/5 times 1/5 is 1/25, sine 5x plus c. And this would be our final answer. Integration by parts is just a formula. Memorize the formula and then apply the formula. This is not a true u substitution because I'm not replacing u with something and du. I'm finding what parts I'm going to use to plug into this formula based on what I was given. Anytime I say d, that means differential. That's why that sine 5x dx is all underlined in green, because that's what I said that dv was equal to. The differential has to be with the dv. Anytime you're using integration by parts, typically you want to let u be equal to something that will go away when you take the derivative, just like the x went away when I took the derivative, and then that left me with a trig function right here that I could then integrate, and the x was gone from the problem. In example 2, what do I want to let u be equal to, and what do I want to let dv be equal to? Do we know how to integrate ln? No, we don't. We know how to take the derivative of it though, don't we? That means that I want to let u be equal to the natural log of 3x. I said typically you want to let u be something that when you take the derivative it goes away. Well, if I let u be 4x, when I take the derivative it goes away. But I can't let u be the 4x, because if it did, then that meant that the ln would have to be the dv and I'd have to integrate it. And I don't know how to integrate a natural log. That's why by default the natural log has to be equal to my u. That's how I made that decision. So if this is u, what is du going to be? Well, the derivative of a natural log is going to be the derivative of the argument over the argument. And when I clean that up, that's just going to give us 1 over x dx. So if u is the ln of 3x, that means that dv has to be equal to 4x dx. So what is v going to be equal to? Well, I integrate both sides to get v. That's going to be equal to 2x squared. So I have the integral of u dv equals uv minus the integral of v du. And until you have this formula memorized, I recommend that you write that formula down. U, we said, was the natural log of 3x. V is 2x squared minus the integral of v du. And then we want to clean this up. And this is bound from 1/3 to 7. So that's going to give us 2x squared ln 3x minus the integral from 1/3 to 7 of, here this x will cancel with one of these x's, leaving us, I guess I could pull the 2 out, just x dx. So that's going to be 2x squared natural log 3x minus, and when we integrate x, that's going to give us x squared, 1/2 x squared, so that 2 times the 1/2. And then our bounds are going to go from 1/3 to 7. So the 2 and the half are going to cancel each other out, and that gives us 2x squared natural log 3x minus x squared from 1/3 to 7. Now we can plug in our bounds. So when I plug in my upper bound, that's going to give me 2 times 7 squared times the natural log of 3 times 7 minus 7 squared minus, and then we plug in our lower bound, and that's going to give us 2 times 1/3 squared natural log of 3 times 1/3 minus 1/3 squared. And then we can clean this up. So 7 squared is 49 times 2 is 98. Natural log 21 minus 49 minus, and then here the 3 times the 1/3 is going to be 1. And what is the natural log of 1? Natural log of 1 is 0. Those go away. So that's going to be 0 minus 1/9. So then that's going to give us 98 natural log 21 minus 49 plus 1/9. You can get a common denominator because you don't want to write this as a decimal. This ends up being 98 times the natural log of 21 minus 440 over 9. Or negative 49 plus 1/9 gives you 440 over 9. And that would be your final answer. Don't make a mistake with the formula. There's a lot of places that you can make a careless mistake if you're not careful. Your handwriting can make you or break you on these problems. The neater you are, the easier it will be. If you start getting sloppy with things, it's easy to get lost in your problem. All right, example 3. Just to remind you, we have the integral of u dv equals uv minus the integral of v du. This is the pattern that we're looking for. So we need to let u be something and let dv be something. What am I going to let u be equal to here? X squared. What is dv going to be? E to the 6x dx. So if u is x squared, what is du? That's 2x dx. Don't forget your differentials. It'll cost you a point. The question was, is there any way in particular that I'm going about deciding what gets to be the u and what gets to be the dv? And the answer is yes. If there's anything that will go away when I take the derivative, that's what I want to let u be equal to. In the last problem, I couldn't do that because I didn't know how to integrate ln. But this time I do. I can do this because when I take the derivative of x, it's going to go away eventually. Back to our problem. So u is x squared, du is 2x dx, dv is e to the 6x dx. So what will v be equal to? 1/6 e to the 6x. So now applying this formula, we have the integral of u dv. That's going to be equal to u, which is x squared, v, 1/6 e to the 6x, minus the integral of v du. And du, we said, is 2x dx. So we're going to clean this up, and that's going to give us 1/6 x squared e to the 6x minus, and then 2 times 1/6 leaves me 1/3 as a constant. I can pull that constant out of my integral, and then I have x e to the 6x dx inside the integral. Now I have to evaluate this integral, and it looks like it's ready to do another integration by parts on, so I need to figure out what I'm going to let u be equal to. So here I'm going to let u be equal to x, du is dx, and then the x is going to go away. dv I'm going to let be the same thing. It's e to the 6x dx, which means that v is still going to be 1/6 e to the 6x. So notice my integral is still in the form, the integral of u dv. That means I can do another iteration of the integration by parts. You may have to do these a couple of times in order to get the integral down to something that you actually can integrate. So this is 1/6 x squared e to the 6x minus 1/3 times, now this is in the form, the integral of u dv, so this is going to be u v minus the integral of v du, and du now is just dx. And this is where you've got to be careful, because you've got to distribute that negative 1/3 across to both of these terms when you clean this up. So that's going to give us 1/6 x squared e to the 6x minus, and then 1/3 times 1/6 is 1/18 x e to the 6x plus 1/18 the integral of e to the 6x dx. Now we're ready to integrate this last term, and we can. So that's going to give us 1/6 x squared e to the 6x minus 1/18 x e to the 6x plus 1/18 times, and then when I integrate e to the 6x, I get 1/6 e to the 6x plus c. So that means that our final answer is as follows. The only thing I had to do to get my final answer was multiply 1/18 times 1/6, and that gave me 1/108. So this would be our final answer for this problem. The question was, did you do the u dv thing twice? And the answer is yes, I did the integration by parts formula twice for this problem. The first time I did it, it worked the x squared down to an x, and then the second time I did it, the x went away, and then it left me with an integral of e to the 6x that I could then evaluate. Now this next example I'm going to show you is a little different, because we're going to have to keep writing down the left-hand side. We're going to have to do the integration by parts formula until we get the same expression on the left for our integrand as we have on the right, and that's because we have two transcendental functions here. So just to remind you, the formula for integration by parts is the integral of u dv equals uv minus the integral of v du. Notice e to the x and cosine x, it doesn't matter how many times I take the derivative, these are never going to go away. So the best I can do is make the integral on the right look like the integral on the left. So we're going to do the integration by parts, and we've got to pick what we want to let u be equal to and what we want to let dv be equal to. And honestly, I don't care which you do, you just got to be consistent each time. So what do you want to let u be equal to, the exponential or the trig function? What would you rather take derivatives of, and what would you rather integrate? You want u to be cosine x, you'd rather take the derivatives of the trig functions, okay? So that's cosine of 3x, and that means that dv then is going to be e to the 4x dx. If u is cosine 3x, what is du going to be? Derivative of cosine is negative sine, but don't forget the chain rule. You've got to multiply by the derivative of the angle as well. And then for v, we're going to get 1/4 e to the 4x. So with this problem, we have the integral of e to the 4x cosine 3x dx is equal to uv minus the integral of v du, and we definitely want to clean this up. So I have to write the integral down again. So we have the integral of e to the 4x cosine 3x dx is equal to 1/4 e to the 4x cosine 3x. And then when I clean this up, I'm going to get minus and negative gives me a plus, and then that's going to give us 3/4 the integral of e to the 4x sine 3x dx. Now I have to do the integration by parts again. The first time I did it, I let u be the trig function. So guess what? I'm going to let u be the trig function again. That means that du is going to be 3 cosine 3x. And dv, we say, is going to be equal to e to the 4x dx. So that means that v is 1/4 e to the 4x. These problems aren't hard, but they are rather tedious. I spend a lot of time just copying down what's already there. Now this is 3/4, and this integral is in the form u dv. So that's going to be uv minus the integral of v du. And I just noticed I forgot my dx here. Anytime you do d's, you need a differential. Now that 3/4 gets distributed across to these terms right here, and that's going to give us the following. Now when I distribute the 3/4, that's going to give me 3/16 e to the 4x sine 3x minus, and then I've got 3/4 times 3/4 is 9/16 integral of e to the 4x cosine 4x. Ooh, that wasn't a cosine x, this was a cosine 3x. Cosine 3x dx. Now what I want you to notice is that I have the same value for the integrand on the left-hand side and the right-hand side. This is an equation because of that equal sign. In order to solve the equation, I would consider these two integrands to be like terms. So I'm going to add 9/16 integral of e to the 4x cosine 3x dx to both sides of the equation. Remember, what you do to one side, you have to do to the other. And this is the part that's probably very different from anything you've ever done before with calculus. But you've added variables to both sides of an equation before. Just think of that integral as if it were a variable. So I have one integral plus 9/16 of an integral, and that's going to give me 1 plus 9/16 is 25/16. Integral of e to the 4x cosine 3x dx equals 1/4 e to the 4x cosine 3x plus 3/16 e to the 4x sine 3x. And now I have to put plus c because I no longer have an integral at the end. I didn't have to put the plus c until I removed the integral completely. The integral is now gone on the right-hand side. So now I got to put the plus c. Is this my final answer? No, because I've got 25/16 of this integral equal to this. In order to get that integral by itself, I have to multiply by the reciprocal, 16/25. But what you do to one side, you want to do to the other, which means that that has to be distributed across. So when I distribute that, I'm going to get that this integral e to the 4x cosine 3x dx is equal to 16 over 25 times 1/4 e to the 4x cosine 3x plus 16 over 25 times 3/16 e to the 4x sine 3x plus c. So 4 goes into 16 4 times, and these 16s are going to cancel out, and that gives me that my final answer is going to be 4/25 e to the 4x cosine 3x plus 3/25 e to the 4x sine 3x plus c. And that would be our final answer. It's not that what we did was any different from what we've done before. It's just that because we had two transcendental functions, you have to keep writing down the left-hand side until you reach a point where the integrand on the right is equal to the integrand on the left. Then we moved that integral on the right over by adding 9/16 to both sides, and then we can multiply by the reciprocal of the constant in front of the integral to get the integral by itself, and that will then give us our final answer. Example 5. We're asked to evaluate the integral from 0 to pi over 18 of x tangent squared 6x dx. Just to remind you, the integral of u dv is equal to uv minus the integral of v du. What do we want to let u be equal to for this problem? We want to let u be equal to x. So du is dx. That means that v has got to be tangent squared 6x dx. Well, if you remember your Pythagorean identities, we can rewrite tangent squared as secant squared minus 1. So if I want to find v, I need to integrate secant squared minus 1. And what is the integral of secant squared? That was the 6x for the angle. The integral of secant squared is tangent, but what about that 6x? What do we have to do with that? It needs to be 1/6. So this is 1/6 tan 6x. And then when we integrate the 1, we get x. So this is 1/6 tan 6x minus x. So this is in the form, the integral of u dv. Notice I'm not changing the bounds. The reason I'm not changing my bounds on these integrals is because I'm not doing a u substitution where I'm changing my variable of integration. These u's and dv's are just part of a formula that I use to help me in integrating. My variable of integration is still x. So this is in the form, the integral of u dv, so that's going to be equal to uv minus the integral of v du, and du in this case was dx, and this is the integral from 0 to pi over 18. So cleaning this up, we get 1/6 x tan 6x minus x squared minus, and now can I integrate this? I'll tell you what, I'll break this into two integrals. We're going to do it this way. This is going to be minus 1/6 the integral of tangent, which I could write as sine over cosine, minus x. And the integral of x is going to be what? 1/2 x squared. I'm going to go ahead and integrate that x. And now I need to distribute this negative across here and here. And I'm going to do a u substitution, and this time it is a righteous u substitution. We're going to let u be equal to cosine 6x. So what is du going to be equal to? It's equal to 6 sine 6x dx. Chain rule. I don't have the 6 there, so I'm going to divide that 6 off, and that's going to give me 1/6 du is equal to sine 6x dx. And there is the sine 6x dx that I need for my du. On part of this problem, I tell you what, I'm not going to change the bounds. I'm going to go back to the original variable just because I've got so many variables with x's here. I don't want to change the bounds on everything. So let's clean this up. We've got a lot to clean up. That's going to give us 1/6 x tan 6x minus x squared. And then I've got this minus 1/2 x squared right here. And then I've got minus 1/6 the integral, and I'm leaving the bounds off because I'm not going to change my bounds. So this is going to be 1/6. Oh yeah, that 1/2 is positive, not negative. You asked, how did I take this 1/2 out? The question was, how did I take this 1/2 x squared out? Well, if you notice, this right here is just the integral. I went ahead and integrated that x and got 1/2 x squared. I actually pulled it out of the integral because I integrated it. This 1/2 x squared was already integrated, but that was negative with a negative there makes that a plus, so I need to make that sign positive right here. The only integral I have going on right now is this integral where I've got the minus 1/6 integral of, and then my du is on top, then that du is 1/6 du over, and then this is my u, the cosine 6x. Do you see that? That's what I said u was going to be equal to. So cleaning this up, we get 1/6x tan 6x. And then minus x squared plus 1/2 x squared gives me a minus 1/2 x squared minus 1 over 36, the integral of du over u. But can I go ahead and integrate du over u? Are y'all okay with that? The integral of du over u is the natural log of u, but what was u equal to? Cosine 6x. Now I'm ready to put my bounds back in the problem that go from 0 to pi over 18. Now we can use the fundamental theorem of calculus to evaluate this integral. When we plug in our upper bound, we get 1/6 times pi over 18. Tangent of, that's going to be pi over 3 minus 1/2 times pi over 18 squared minus 1 over 36 natural log cosine of pi over 3 minus, and now we plug in our lower bound. Our lower bound is 0, so that's going to be 1/6 times 0 tan 0 minus 1/2 times 0 squared minus 1 over 36 times the natural log of cosine 0. And let's clean this up. So this tan pi over 3 ends up being the square root of 3, and cosine pi over 3 ends up being 1/2. Cosine of 0 is 1, and the natural log of 1 is 0. So this term goes to 0, this term goes to 0, and this term goes to 0. I don't have to worry about any of those terms. So that's going to give us pi over 6 times 18 is 108 times the square root of 3 minus, and then I get pi squared over 648 because that's 18 squared times 2 minus 1 over 36. And then the natural log of 1/2 I could write as this, or I could write plus 1 over 36 natural log 2. Your call. 1/2 could be written as 2 raised to a power of -1, and then that negative would cancel out. So I would either accept this as an answer or this with a plus 1 over 36 natural log 2. Either one of these answers will work. The only thing I did was I used the power rule here to rewrite the natural log of 1/2 as negative natural log 2. When you're checking your answers in the back of the book, if you have either one of these and they have the other, as long as your answer can be algebraically manipulated into their answer, your answer is fine, and you would get full credit for it on the test. Just keep that in mind when you're checking your answers.